Now that's for just one subset. And remember, when you're building a decision tree, at each node you're going to have a bunch of children, so you're actually going to have multiple subsets. So what we're going to do is we're going to take an average of the entropies for each one of the subsets that we end up with, right? So if we were splitting on attribute A, and attribute A had a number of values v, what we're going to do is we're going to split the overall set into subsets S of v, and then measure the entropy for each one of the subsets. So that's your HS of v. And note what we're also doing here is we're multiplying those entropies by some numbers. So what are those numbers? Those numbers basically tell us how big is each one of the subsets. So the numerator, that's the size of the subset. Right? So if V was rainy, for example, that tells us how many rainy days we had in our set that we were splitting. And S is the total number of examples before we did the split. So now, why are we doing that? By doing this, you're computing an average of the entropies for each of the subset, but you're giving more weight to bigger or smaller subsets. Bigger subsets. Okay? Now, why is that important? Why does it make sense? The reason it makes sense is maybe one of the subsets has only one instance in it. So maybe there was only one rainy day in your entire data set. That subset would be pure by definition, right? If there's only one instance in a subset, it has to be pure. It was either positive or negative. So that subset is guaranteed to be pure, but it's a very, very small fraction of the data. And what you want to do is you want to reward the kinds of splits that produce pure subsets for large numbers of examples, not a pure subset consisting of one example. So that's what this part accomplishes. It gives a higher weight to the entropy of a larger subset and a lower weight to smaller subsets. So overall, what this part tells you is what is the average entropy, what is the average sort of impurity after the split biased towards the larger subsets. And what we do is we take that value and subtract it from the entropy that we had before the split. And the difference between the entropy before the split and the entropy after the split is called information gain. In computer science, in statistics, they call it mutual information. It's mutual information between two random variables. It's the attribute A that you're splitting on, and the class labels, the positives and the negatives, the targets that you're doing. Okay, so let's look at an example. We're splitting on wind. We had our initial set S with 9 positives and 5 negatives, and we split it into 2 subsets. One subset had 6 yeses and 2 no's. Another one had 3 positives and 3 negatives. So what's the gain value in this case? The entropy before the split. So it's just P log P for the positives minus P log P for the negatives. So that works out to be 0.94. That's how many bits you need to, that's how many bits of uncertainty you have before the split. It's 0.94 bits. Now what happens after the split? For the weak subset, we have the entropy of 0.81, and that again is just 6/8 the probability of positive, 2/8 the percentage of negatives, and we just plug them into the entropy, and we get 0.81. And then for the second one, we already know what the entropy is, right? It's got to be 1 because it's a 50-50 subset. So the entropy there is 1. So we have 3 entropies: the entropy before the split, and the entropy of the 2 subsets after we split on the wind attribute. And then we put them all together into the gain of the attribute. And the gain is you take the entropy before the split, so that's 0.94, and you subtract from it the entropies of the two subsets after the split, so that's 0.81 and 1.0, and you assign to them the weights according to their size. Right? So 0.81 has a higher weight because it has 8 examples falling into that subset, and strong has only 6 examples, so it has a slightly smaller weight in the average. Then you subtract the two and you get 0.049. So that is the information gain of the wind attribute at the root node. Now, how do you use that for determining which attribute to pick? Yes, you want to maximize the gain. So really what the gain tells you is before you did the split, you were pretty uncertain about which things were positive, which things were negative. After you did the split, you are more certain, and the gain tells you how much more certain the positives and negatives become if you pick that attribute. So what you want to do is you want to take every attribute that you have in your data, compute information gain for that attribute, and then select the attribute that has the highest information gain. Because that's the attribute that's going to reduce your uncertainty the most. That's the attribute that will lead to the purest possible split out of all the attributes that you are that you're currently considering. So that's the basic idea, and that's how gain is used. Is that all clear? Any questions before we move on?
Quite slow.
So the comment is quite slow. We're not even thinking about computational expense now. So yes, doing it brute force is quite slow. You can build data structures that make it not quite so slow. But we're not even considering the speed at this point.
It's only done at the root level?
The question is it only done at the root level? No, you do it recursively. So you do it for the root. That ends up giving you several branches, and then you recurse. So you go to the left branch, and you repeat exactly the same thing. You take every attribute except one. Which one do you not take? The one that you've just split on, right? So in a decision tree, you never have to look at the same attribute twice unless the attributes are real valued. So for categorical attributes, you never have to look at it twice. So you look at all the attributes and recompute the gain for them and use the attribute with the maximum gain, but now you're working in a subset, right? So now you're actually, it's divide and conquer. Now you're working with a smaller subset of examples, and it's actually going to be easier to split it, hopefully.
I'm sorry, I actually meant that do you select, when you are selecting the root attribute, do you first calculate the entire gain by recursing down the entire tree and then selecting the attribute? Or?
Okay, so the question is, when you compute the attribute for the root, do you recurse all the way down the tree in that step? No, you don't. You just consider a one-level split. So if you tried to recurse, the complexity of that would be in the number of possible trees, and that's intractable. You cannot do that.